Welcome to this video on modelling with differential equations. This is the first one, which is on first order differential equations. What we're going to do here is just an extension of what's in the A-level maths syllabus, where we do some modelling using differential equations. The only way that's within the A-level maths syllabus of solving differential equations is by separating the variables. For further maths, we now have another technique where we can use an integrating factor. So there are more equations that we should be able to solve. We've got two examples in our course workbook, so we're going to go through those. The first one, we're given a differential equation. So we've got a rocket burning fuel, and we're given an equation involving the velocity and time. We've got to show that V is this expression here. So effectively, part A is asking us to solve this differential equation. And then we're going to use what we found in B and in C. So let's go ahead and solve this differential equation. If you remember back to using integrating factors, what we need to do first of all is we need to isolate that dv by dt by itself. So we're going to divide through by this bracket. So for part A, we're going to start off by getting dv by dt plus 1 over 25 minus 2t times v is equal to 100 over 25 minus 2t. So we've now got it in the form where we can get an integrating factor. In fact, it is possible to do this by separating the variables. So we could have started off here, rearranged, brought our v over there, and separated the variables. If you do that, you're going to have to do a lot of work with logs to get it back into the form v equals. So I'm not necessarily saying it's harder, but we'll stick with the integrating factor method here. So integrating factor is going to be e to the integral of 1 over 25 minus 2t dt. When we integrate that, we get e to the minus a half ln of 25 minus 2t, which is equal to 25 minus 2t to the power of a half. We'll leave that with a with a power for the moment rather than rewriting it with a root, because it's a little bit easier to do the integration if we leave it that way. So we're going to multiply through by this integrating factor, so we get 25 minus 2t to the power of a half dv by dt. Sorry, to the power of, that should be minus a half. There we are. I knew there was something wrong there. The power of minus a half plus, let's now write this as a bracket, 25 minus 2t. This is the power of minus 1 times the power of minus a half is minus 3 over 2. V is equal to, on the right hand side, 100 times 25 minus 2t, also to the power of minus 3 over 2. So what are we going to do now? We're going to integrate. So on the right hand side, we're just going to get v times 25 minus 2t to the power of minus a half And if you just notice that when we differentiate that, we get the -1/2 times the -2, which was why we don't have any constant factors here, is equal to, if we integrate on the right-hand side here, we're going to get 25 minus 2t to the power of -1/2. And again, if we were to differentiate that, we get -1/2 times -2. So we don't need to multiply this 100 by anything. We just get that 100 there. And then absolutely crucial that we remember that plus c. If we divide through by this 25 minus 2t to the -1/2, or in other words, multiply through by 25 minus 2t to the power of 1/2, we're going to get v is equal to 100 plus c, 25 minus 2t power of 1/2. Now we need to find the value of this this c. So we're going to look at where it tells us what values to use in the question. It says the rocket is initially at rest, so that means when t is equal to 0, v is equal to 0. T equals 0, v equals 0. So 0 is equal to 100 plus c times 25 minus 0 to the power of 1/2. 25 to the power of 1/2, so that's 5c. So c is equal to minus 100 over 5, which is minus 20. And now we can write, let's just move that up the page. Now we can write v is equal to 100. We've got minus 20 now, minus 20, and we can turn that into a square root. So root 25 minus 2t. Let's go on to another sheet of paper here. Oops. So for part B, we need to find the speed of the rocket when t is equal to 12. So t equals 12, v is equal to 100 minus 20 times the square root 25 minus 2 times 12 is 24. Square root of 1, so 100 minus 20 is equal to 80 meters per second. For C, we're being asked what happens for t is greater than 12.5. T is greater than 12.5 means that 25 minus 2t is less than 0. So we can say, v, if we try and take the square root, would be complex. So v is not real. What does that mean? Well, it makes no sense really, does it, for a velocity to be a complex number. So it's saying that the model cannot be used for t is greater than 12.5. So the model cannot be used for t is greater than 12.5. Why is that? We could look back at the question, and it does say the rocket of mass 25 kilograms burns fuel at the rate of 2 kilograms per second. I don't know whether that how much of that 25 kilograms is itself fuel, but it suggests that the fuel is not lasting beyond t is 12.5. Fuel only lasts this long. Okay, let's go on to question 2. Let's find that now. There we go. So question 2 is perhaps more typical of an exam question in that although we're given a differential equation here, we've got to show that the situation described in the question can be modelled by this differential equation. Sometimes you might be asked to come up with a differential equation yourself. So we've got a storage tank containing 1,000 litres of pure water. Liquid is removed from the tank, and that's at a constant rate of 30 litres per hour. And we're adding a solution of copper sulfate to the tank at 40 litres per hour. And we're interested in the mass of copper sulfate, which is given by X, in the tank after T hours. We're assuming that the copper sulfate immediately disperses through the tank on entry, so the solution coming into the tank. So we need to think about what's going in. So mass of copper sulfate in, well, that's going to be, we've got 40 litres and each litre contains 4 grams, so it's going to be 4 times 40 is equal to 160 grams per hour, G per hour. But then we've got it draining out as well, so the decrease, so out, it's going to be, well, it's 30 litres per hour times whatever the concentration of copper sulfate is. So 30 times concentration of the solution in the tank, which is 30 times, well, we need the mass of copper sulfate in there divided by the volume. So X over, what's the volume in the tank? Well, it starts off at 1,000. We're adding in 40 litres every hour, so plus 40 T, and we're taking out 30 litres per hour, 30 T. So that's equal to 30x over 1,000 minus, plus 10t, which is 3x over 100 plus t. So now we can say that the rate of change of the mass of copper sulfate, so change is equal to in minus out, which is 160 minus 3x over 100 plus t. And what is the change? Well, the change is dx over dt. So we've shown that this equation models this situation. Okay, so now it says, hence, find the number of grams of copper sulfate in the tank after 6 hours. So what we need to do now is we need to solve this differential equation, and then we're going to substitute in t is equal to 6. So we're going to say dx by dt is equal, plus 3 over 100 plus t x is equal to 160. And we're going to find an integrating factor that is going to be e to the integral of 3 over 100 plus t dt. If we integrate that, we're going to get e to the 3 ln of 100 plus t, which is 100 plus t cubed. I'm going to go to this fresh sheet of paper now. Continue the previous one, actually. So once we've got that integrating factor, we're going to multiply through both sides by that. So we're going to have 100 plus t cubed dx by dt plus 3x 100 plus t squared is equal to 160 times 100 plus t cubed. Integrate both sides. This is in the form of the derivative of the product rule. So we're going to get 100 plus t cubed times x is equal to, on this side, we've got 100 plus t to the power of 4. So we need 40 here. 4 times 40 gives us that 160 when we differentiate, plus c. Now we need some initial conditions to find the plus c. In our question, it told us that the storage tank initially contains 100 litres of pure water. So that means there's no copper sulfate in there. So at t equals 0, x equals 0. So we've got 100 cubed times x is equal to times 0. There we are. Times 0 is equal to 40 times 100 to the power of 4 plus c. So 0 is equal to 4 times 10 to the power of 9. This is 10 to the power of 8 times another 10 there, plus c. So c is equal to 4 times minus 4 times 10 to the power of 9. If we rearrange this, we get x is equal to 40 times 100 plus t, then plus c divided by this, so minus 4 times 10 to the power of 9 over 100 plus t cubed. So there's our expression for x there. Right, sorry about that. That's gone a bit in the wrong place. For B now, we're asked to find the number of grams of copper sulfate after 6 hours. So after 6 hours, t equals 6, we've got x is equal to 40 times 106 minus 4 times 10 to the power of 9 over 106 cubed. and that comes out to 881.523, which is 882 grams to 3 significant figures. 182 grams. The very last part of this question, typically a 1-mark part of an exam question, asks us how the model could be refined. Well, we need to look back at the assumptions in the question, and probably the one to focus on here is that they've assumed that the copper sulfate immediately disperses through the tank on entry. So that's unlikely to be the case if you've got a tank maybe where the input is at the top and the liquid is flowing out down at the bottom or something like that. There will be different concentrations throughout the liquid. So we could say for C, consider different concentration levels in different parts of the tank. Or you could say something about consider the solution not immediately dispersing throughout the tank, or something along those lines. Okay, that's it for this first video on modeling with differential equations. We'll go on in the next one to consider what happens when we have second order differential equations. Thanks for listening. I hope this is helpful.